Hello and welcome to a discussion of performing welding simulation analysis in Abaqus using the Goldak flux. What we're going to talk about today is using the tool QustomWeld, which has been developed by the company called QustomApps. So before we get into the actual FEA model, I want to give a little bit of background about Goldak and how we're going to implement or how that's implemented within QustomWeld, and then we'll go and look at an example model. All right, so Goldak is just a way of representing the heat flux that is put in when when depositing a weld into a structure. So the standard shape is this double ellipsoid, which has an ellipsoid shape from the center of the torch to the front of the torch, and then a separate ellipsoid shape from the center to the back of the torch. And it's essentially defined by these parameters A, B, CF, which is in the front of the torch, and then CR, which is toward the back of the torch. So with those quantities, we will develop a tool within QustomWeld that can manage the flux intensity based on this shape. So the standard Goldak equation that represents this energy distribution is as we see here. And then what we're going to do is when we evaluate that integral, basically it's integrating this flux intensity to get the amount of energy put in via the current, voltage, and efficiency. And when we do that, we get some constants. We boil all this down to a number of constants. And the way we solve for those constants is making this assumption that at these distances of A, B, CF, and CR, the flux intensity is dropped by 95%. So when we put that in as boundary conditions, we can actually solve for these constants A, B, CF, and CR, and then we can reduce that equation into a slightly simpler form. But essentially, we're going to solve these equations, and these equations are what we're going to use to define the flux as we put them onto the Abaqus elements. All right. So now one thing with Goldak is that it is, we have an elliptical shape, but that is dependent on how it's oriented. So I just want to briefly mention with QustomWeld, this orientation is defined automatically. There are a couple of ways by centroid. Essentially, if this is the torch path, the normal is assumed to point from the torch path into the centroid of the bead, or just by adjacent faces. If we have two facets here, we'll just average the normal of those two. So either way, they're often very similar, sometimes a little bit different, so both methods can usually be used. And then you can also specify them manually by reading from a text file, a CSV file or something. All right, so just a quick mention on the normals. All right, so the problem we're going to look at is a paper that was written, basically two papers, and they discuss the same model with the same geometry and materials, just by two different authors. So it's a 6 bead plate problem, and the mesh is fairly coarse, so it runs within a couple of hours. So it's a very easy problem to run, and it has some experimental data with it. And this particular benchmark just has temperature data. It doesn't have any stress or strain data from the experiment, but it does have the temperature data. All right, and what we're going to see is we're going to kind of jump to the results that we'd gotten with QustomWeld, and then we'll go back and see how the model was built. So we compare it with some work that David DeWeese did, and just a couple plots of the S33 strains. We see very, very similar profiles, and same with S11 strains, very similar profiles. So this is just kind of validating our process, and then just a quick mention about how long it takes to run this. Now the stress analysis usually takes longer than the heat transfer, but there's not a lot of stress linearities in the stress strain curves, as we get closer to melt. So those haven't been too acute. So basically, 5-6 hours to run a continuous, and then we compare with doing the analysis in 2D and with chunking. And we'll see later in other demos or other talks how we do chunking. But just for the continuous Goldak analysis, we're talking about 5 or 6 hours to run. Okay, so let's look at the model and how we created this in QustomWeld. All right, like I said, QustomWeld is a tool. It's a plugin that's part of Abaqus CAE. Okay, and it has the model tree. So here we've got a user's manual, we've got workshops, some examples, and then some tools for color coding and output and highlighting, and one for creating path plots. All right. So when you define a model, you start off just defining the unit system, just a few things, and then defining defaults like your film and radiation conditions. All right, and then we'll go through materials. So you define your material properties in Abaqus CAE, stress strain curve and all of that. But we have to add a couple of quantities based on the material, and that's what its melt temperature is and a cutoff temperature. So the melt temperature, basically that's an initial condition when we activate the beads. We activate them at melt. So and then the cutoff temperature is, this just says that after a certain temperature, any increases or decreases in temperature do not affect the thermal strains that are calculated. So we just cut off the thermal strains at some point. So we have to enter these two quantities for the material. Then we have to enter the base material, which is essentially everything except for this bead area. So we just pick on that, and then we select the default element types. All right, and finally we get down to actually defining the weld, which in this case contains 6 beads. So I want to turn on color coding just to make it a little bit easier to see. We can turn on the mesh if we want. All right, so the way we would do this is, I'm not going to go through the process since it's already been done, but essentially we would pick on create a bead. We would pick on the geometry of the bead. In this case, we picked the cell because we have the cell geometry. The path, different ways to assign the path. This case is element edge picking, which, let's turn on the, so let's say that our path was along here, and I will actually highlight our path. Oh, sorry, that's for bead 1. Let's actually edit bead 6. So our path, what we could have done is that we could have put a partition in here, partition the geometry, but it's usually a little bit easier just to pick a single edge here, and then it automatically selects the line of nodes. All right, so that's what was done here, and then a starting point, whether we start the weld from here or here. And when we actually lay down the beads, we can always reverse it, so that's not that important. And then the different ways of calculating the normals, this is based on adjacent faces. So if I want to highlight the normals. Okay, so just turn on the normals if we want to see the directions of the torch. All right, so then we would go through and do that for all 6 beads. And then once they're all defined, then we would see that we've chosen the base, we've chosen all the beads, and then once that's done, you'll see a green check mark. And now we want to assign it to a robot. So the way we put down beads is we create a robot. Even if you aren't doing this with a robot, it's just a manual person doing it, we still assign it to a robot. So when we create a robot, we give it some default controls, like how fast it is, dwell time is like before when it first starts the bead, how much time do we heat up the first point before we start to move. And then there's some defaults, torch type Goldaks versus constant flux, continuous versus chunking, and then the shape of the torch. So all these are the defaults. And then when we actually assign the weld to the robot, then we can override all of those defaults bead by bead. So like in this case, we have different torch speeds, different voltages, currents, and so on. And then this is how we do the analysis. Torch type, torch placement, these are all continuous. So the gray color shows things that are not editable. So energy ratio, that's just the ratio of how much energy we're pumping into the system compared to how much it takes to melt a single bead. So we see I have a pretty high energy ratio. That means we're going to easily melt the entire bead as we're going down there, and it'll melt some of the underlying bead as well. So anyway, so these are all the controls for each individual bead, how they're entered. All right, and then we have these if we just don't want to display everything, you know. So all right. So when we defined it to a robot, all we've defined so far is how the parameters of the bead, but not really how they're going down. You know, they're maybe the weld speed, but not when it goes down, you know, which one goes first and so on. So to do that, we generate a weld scenario. So when we create a scenario, it initializes it, it sets a bunch of defaults, but then we go in there and we'll want to change it. So we'll look at robot 1, and what we're going to look at is say, all right, for this robot, we have one weld, lone weld, we have for the bead 6s, and how we're going to put it down, we can either do sequential, simultaneous, or expanded. So in this case, expanded, and we'll see what that means as we get to the next step. And then this is where we can change the torch direction if we want, right? We saw here's our bead 1, and we can change the torch direction. If you see this yellow arrow, that tells you where it starts. See, it starts here, and so if we want to reverse the directions, we can. And then this just tells us our total time, and then we're going to put a cool down between the beads. So this is just saying a 2-minute cool down, and then it just gives us a sum of the times. Okay, so this will give us this will tell us how this particular robot is going to put down this particular weld. All right. And then finally, there's a summary. If we have more than one robot, we can kind of manage how the robots put them down, and whether they're sequential or one robot after another, and so on. All right. So in this case, we don't have to really change anything. And then finally, we go to an analysis. This is where we set up our Abaqus analysis. And again, let's cut down on the number of columns displayed. So this just tells us, okay, we've got the sequence of how the robots are putting the welds down. How are we gonna set the analysis controls? So we have for any given weld, lone weld, in any given bead, we have in that step, we're going to have the maximum allowable number of increments is 5,000. Should be able to do it in a lot less than that. So this is the maximum heat up increment. So we're going to set those time increments and the maximum cool down. So typically we're going to have larger cool downs. So all the gradients, when it's heating up, it's moving. So there's huge gradients that are changing all over the place, right? But when we cool down, we're cooling down over, a 2-minute period. Initially there will be some high gradients, but they'll start to dissipate very quickly. So we can really open up the time increment. This time increment, we want to try to limit that time increment. So, if we're doing a Goldak, continuous placement, we don't want a time increment to be more than, like a fourth of the time period it takes for the torch to traverse the length of itself. So if the torch is 10 millimeters, we don't want to take a time increment in which the torch moves more than 2.5 millimeters. All right. So that's the heat up time increment, cool down time increment. Then there's the maximum allowable heat transfer change. So we're going to put a very large heat transfer change. This is in transient heat transfer analysis. This kind of controls the time incrementation, but we're actually going to control it through the maximum time increment. So we're going to allow very large temperature changes because we have such huge gradients. All right. Now we can have that a little bit, put a little bit tighter controls on that when it's cool down. So, no need to have such a large gradient. And then we have some quantities for output requests. So we want to have quite a few outputs. Now we could do intervals or frequency. In the heat transfer analysis, we're going to do write a lot of data, just because the stress model needs to be able to interpolate those temperatures, so it needs a lot of points to interpolate accurately. All right. So these are all the quantities for the stress or the heat transfer model. So we can then look at the stress model, the same kinds of things: max time increment, heat up, and so on. All right. So once all that's entered, then we can run the analysis, and then we can view the analysis. So what I'm doing is I just put a limit on the temperatures. We're going to look at the temperatures for 1600 degrees and just do an animation. You'll notice there's a number of elements out in front. Now I don't have the elements turned on, but we activate all of these elements at ambient temperature, and then we're heating the beads up and behind those activations. Okay. Now the stress model is going to be different. We have these, when we're activating in the heat transfer model, we're activating at ambient. But when we go to the stress model, let's open that up. So let's just first look at the temperatures just to see how we're importing those temperatures in. So we're still going to have the same max. Oh, I could slow that down a little bit. That's a lot. It's going to process a lot faster just because there are a lot fewer frames stored in the stress model. All right, so then once it gets up here, okay, so you notice there aren't all those elements out front. So when the elements are activated in the stress model, they're activated at melt temperature. Now these gradients are going to be away from melt temperature. So the initial condition, the initial temperature that's used in Abaqus is actually the melt. And then there's a delta T for every element. So there's a strain that's calculated from that. So it works out well the way Abaqus does it. That strain is going to be ramped down over time. So, if, let's say that temperature is above melt, as that element cools down to melt temperature, that strain will end up being ramped down to 0 once it gets to melt temperature. Right? And same if it's activated at a temperature below melt. If it heats up to melt, it'll go back to 0 thermal strain. But then if it's, let's say it's slightly less than melt, it'll have a delta, a thermal strain built in, and that thermal strain will build up as it cools down further. All right. So here's our temperature with the stress model, and you can see this. We calculate it at fewer increments, so we can do. Let's turn off the maximum value. So we can look at. Let's actually look at MESA stresses as they grow over time. All right, or we can look at individual stresses. Okay. But you'll see this classic kind of V shape for a plate. So we get very nice stress results with this. All right. All right, so that was a kind of a quick summary of how we would do Goldak, use the Goldak flux to analyze a plate with Abaqus and CustomWeld. All right, thanks for your time. I appreciate it.